Hi everyone, in this lesson we're going to be looking at inverse functions. And an inverse is something that undoes something. So if we have an original function like y equals 2x plus 3, and we put a value into it, let's say we put 1 into that, we would get an output value of 5. Well, if we put 5 into the inverse function, we would get an output value of 1. So what you can think of it as it's undoing something. It's an inverse. It undoes what the other does. You can think of this as two machines. If the machines are inverses, then the second machine will undo what the first machine does. And I have an example here. You input 1, you get an output of 5. You take 5, you put it into the inverse, you're back where you started. We're also going to use some one-to-one or many-to-one descriptions. One-to-one means for every value of x, there's only one y, and for each y, there's only one x, right? One-to-one functions satisfy the vertical line test and the horizontal line test. This means that no vertical line can meet the graph more than once, and for the horizontal line test, no horizontal line can meet the graph more than once. You probably remember from your Algebra 2 days the vertical line test. That's a visual way to determine if a curve of a graph is a function or not. Right? If we hit it in more than one place, then that graph is not a function. So we have a one-to-one example here. If a function is one-to-one, it's going to pass the vertical line test and the horizontal line test. Meaning if I draw a vertical line, I'll only hit the function in one place. Anywhere I want to draw that vertical line, I would only hit it in one place. And the same with the horizontal line. Wherever I would draw a horizontal line, I would only hit the function in one place. That's a one-to-one function. Here we have a many-to-one example. So we have f of x equals x squared. It fails the horizontal line test because we're hitting the function in two places, but it does pass the vertical line test. Anywhere we are to draw a vertical line, we would only hit it in one place. So what does this mean? This means that our original function, y equals x squared, it is a function. But if I were to take the inverse, and I would be able to find the inverse algebraically, but that inverse would not be a function, right? So the horizontal line test is telling me that this graph, this equation, y equals x squared, would not have an inverse function. Some properties of inverse. Well, first of all, we have notation. If you say f raised to the -1 power, that is notation for inverse. It has to satisfy the vertical line test, and inverses are always going to reflect over the line y equals f of x, or usually we say y equals x. That if you're looking at a graph, and let me draw one really quickly, the equation of the line y equals x, I usually draw it as like a dashed. Inverses will reflect over that line. Something else to notice, since the inverse undoes the function, if I were to take the inverse and input it into the original, I'm going to get x, assuming this function is in terms of x. And if I were to take the function and input that into the inverse, the same thing would happen. I would get x. The function y equals x is called the identity function because it is its own inverse, and when its inverse is found, it maps right onto itself. All right? So we're going to take a look at a lot of examples here. This is just really kind of setting you up with understanding all the vocabulary. Right, we have our first example here. We have this function y equals 5x plus 2. If we want to find the inverse, we're going to just switch the x and the y. So you're going to switch these two values. So we're going to have x equals 5y plus 2. Now we solve for y. So subtract 2 from both sides. and divide both sides by 5. So our inverse is x minus 2 over 5. All right, so that's how we would find the inverse algebraically, all right? And this is the original function right here, graphed. This is our new function graphed. And you could see that our inverse reflects right over the line y equals x. Another important note here, domain and range. If f of x has an inverse, then the domain of the inverse is equal to the range of the original function. And the range of the inverse is equal to the domain of the original function. All right, so let's do one a little bit slower here, a little bit more carefully. We have this function 2x plus 3. So first of all, I'm just going to show you algebraically how to find the inverse function if we needed that. So we have y equals 2x plus 3, and we are going to just switch the x and the y. So that becomes x equals 2y plus 3. So x minus 3 equals 2y. Divide both sides by 2. So x minus 3 over 2 equals y. So that is the inverse of our original function. Now, it wants us to, on the same set of axes, graph f and its inverse. Well, I don't know about you, but I really don't like the idea of like looking for values with the inverse. I like the original one. It's just the equation of a line. I'm just going to use some points from that. And because I have an inverse that I also need to graph, I can just flip the coordinates for my inverse, and that's how I'll demonstrate graphing that. So let me show you what I mean. So first of all, let's put some values into our original function. I'm just going to pick some random numbers here for x. I'm going to pick -2, 0, and 2. And if I put -2 into my original function, I'm going to get -1. If I put 0 into my original function, I'm going to get 3. And if I put 2 into my original function, I'm going to get 7. Right, so this is the y equals 2x plus 3. And my inverse function is going to be y equals x minus 3 over 2. Now, like I said, that x minus 3 over 2 doesn't look like it's a good time picking x values for that. It's a little more tedious. But if you remember that you can just switch the coordinates for the inverse, it's going to make your life much easier. So all of the x values would be the y values in my inverse for these coordinates, and all the y values would be my x values for these coordinates on my inverse. So let's do the points for the inverse. So -1, -2, 3, 0, and 7, 2. Makes it really easy. All right, so I'm going to graph my original function and my inverse, and let's take a look at that. All right, so my graphs are drawn. Now, if I did it correctly, my inverse function should reflect nicely over my line y equals x. So let's just draw on the line y equals x. We could see that the red graph, the original function, perfectly reflects over the line y equals x to be our inverse function, which is the blue graph. All right, so now we're being asked to use composition of functions with an inverse. All right, so what does that mean? First of all, I'm going to just rewrite this. I'm going to put the inverse function inside my original function. And if you remember how to do composition of functions, the way I usually explain it is I put a box wherever there's an x. So my original function is 2x plus 3, so I'm going to put a box. I'm going to fill in the box my inverse function. So this is my inverse function. So let's put that here. And now we're going to simplify that. Well, when we do that, the 2's cancel. I end up with x minus 3 plus 3. And what's my final answer here? X. So it says check that f composed with f inverse and f inverse composed with f is equal to x. All right, so we did the first part of that. Let's do the second part. I'm going to do f inverse, and this time I'm going to put in the original function. So the inverse function is my lead. So I'm going to put a box wherever there's an x in the inverse function. Now inside the box goes my original function. The original function is 2x plus 3. And then we're going to simplify that. Well, 2x plus 3 minus 3 gives me 2x, still over 2. And 2x divided by 2 gives me x. So now I've successfully completed part B. All right, so we have some practice here. We have a function, 3x plus 1. On the same set of axes, we're going to graph y equals x, the original function, and the inverse function. So the first thing that I'm going to do is I'm going to find the inverse off to the side. My original function is y equals 3x plus 1. For my inverse function, I have to switch the x and the y. So I get x equals 3y plus 1. Solve for y. Okay, so on my axes, I'm going to do my original function, my inverse function, and I'm going to also graph y equals x. My original function is 3x plus 1. I'm just going to pick the same x values I picked in the last example. I'm going to use -2, 0, and 2. But if I put -2 in there, I'm going to get -5. Right, -2 times 3 is -6, plus 1 is -5. 3 times 0 is 0, plus 1 is 1, and 2 times 3 is 6, plus 1 is 7. For my inverse, I'll do those coordinates in blue. You're just going to flip the points. Nice and easy, okay? And then for the line y equals x, this is a really easy graph to do. If you put, let's say, a -2 in here, you're going to get -2 out. Put 0 in, you're going to get 0 out. If you put 2 in, you're going to get 2 out. Right, so I'm going to draw that line y equals x first. And now I'm going to draw in my f and my f inverse. Okay, I have my graphs drawn, and I know I did it correctly because my original function reflects over the line y equals x. Right now, it says find f inverse using variable interchange. Really, that's just IB notation. We're doing what we did right up here. Okay. I demonstrated that there, but I'll just use the appropriate notation here. Variable interchange, just switch the x and the y. Okay, part B, we're given a new function here, x plus 2 over 4. On the same set of axes, we're going to graph y equals x, the original function, and the inverse function. I'll use the same coordinates that I used before for my y equals x, -2, -2, 0, 0, 2, 2. Right. Now I'm going to pick some values to put into my original function, x plus 2 over 4. I want to make it really easy on myself. I don't want to deal with any fractions. If I put -2 in there, I'm just going to get 0. If I put 2 in there, I'm going to get 1. And let's see, I need something divisible by 4. If I put 6 in there, I'm going to get 2. We switch the points for the inverse. And we're going to put all 3 on the graph. All right, I have my graph. I can see that my original function reflects over the line y equals x. So I know I've done it correctly. We're going to use variable interchange to come up with the inverse of the original function. So let's go ahead and do that. So f inverse of x is going to be x equals y plus 2 over 4. Solve for y. All right, and that's it for this page. We're going to use the horizontal line test here. For a function to have an inverse function, no horizontal line can cut its graph more than once. So we're trying to decide if just by looking at this, will the inverse be a function? We can find the inverse algebraically, but that doesn't mean it's a function. So which of the following functions have inverse functions? Anywhere I draw a horizontal line, I'm only going to touch that graph in one place. So this function has an inverse function. Looking at the next one, in this graph, I do easily, anywhere I draw a horizontal line, I'm hitting it in more than one place. So this does not have an inverse function. And lastly, we can hit this graph in more than one place when we draw a horizontal line. So this does not have an inverse function. All right, moving on to number 3, it says draw the graphs of y equals x and the inverse. In each case, state the domain of the original function and the inverse. Well, domain is much easier to do once we have the graphs. We'll take care of all the graphs first before we examine the domains. All right, well, first of all, for the original function, we have some coordinates. We have a coordinate at -2, 0. And we also have a coordinate at 0, 5. So that means for the inverse function, we have coordinates at 0, -2, and 5, 0. So let's plot and draw that. And we're just going to guess here. We don't have an exact, precise graph, but we'll fill that in. All right, now let's examine the domain. The domain of the original function, and remember, domain deals with x values. Our domain starts at -2 and ends at 0. And it includes the values because these circles are filled in. So we're going from -2 to 0. Now, the domain of the inverse function, again, we're looking at the values of x that are going to be included. We start at 0 and we go over to 5, right? Maybe it would be helpful just to label that. We start at 0 and we go to 5, including 0 and 5. All right, let's take a look at part B. The original function has coordinates at, so our inverse function, let's draw that graph. Okay, and I did forget for part A, and I'm just going to add this in, we're being asked to draw in that line y equals x. That's always good practice to make sure that there's a reflection. So if we look at our domain of our original function, we want to know what values of x are included. Now there's an arrow at the end of this one, so you have to notice that. And there's a filled in circle at the beginning, right? So our domain is going to be everything to the left. That means negative infinity of x. Let's write that down. Through 0 and including 0, right? So everything to the left, it's going everything to the left including 0. Now if we look at the other graph, right, if we look at the inverse graph, we start at 4 including 4 and we go to positive infinity. right? We start here and we're going right. And we have that arrow in the end. That's why we have positive infinity. We have the arrow here. That's why we have negative infinity. Okay, taking a look at letter C. We're going to identify some coordinates on our original graph. So we have a coordinate at -3, 0. And we have a coordinate right here at 0, 1. For our inverse function, we're going to have a coordinate at 0, -3, and 1, 0. Let's draw that graph, and also we need to include y equals x. Okay, we have our graphs drawn. Let's take a look at the domain of the original function. We have arrows on both ends of our original function, so we're going to get everything to the left and everything to the right, so our domain is going to be all real numbers. And if we look at our inverse function, we have arrows on the ends, right? So our domain is also going to be all real numbers. And we assume those arrows are there because the original function had arrows on the end. Okay, taking a look at number 4. Show that the function y equals 3 minus x is its own inverse. If a function is its own inverse, we say the function is self-inverse. Right, so we want to just find out what the inverse is, and it should end up being 3 minus x, just like the original function. So our inverse function is going to be x equals 3 minus y. Solve for y. So we get right, and so in IB, when they use that word show that, that's what they mean. You're just demonstrating. They're telling you it's its own inverse. They're giving you the answer. You're just basically doing like a little proof to show that that function is its own inverse. All right, for number 5, we have another one like that. It says, given the function, show that f is a self-inverse. So we're going to do the inverse of that function. So the original function was y equals 1 over x. I mean, you think of it like this, that f of x just means y. So when I switch those for the inverse, I get x equals 1 over y. Right, we're going to solve for y. So I'm going to multiply both sides by y. So I'm going to get yx equals 1, and then divide both sides by x. So we get y equals 1 over x. And we've shown it. So we knew the answer when we started. We just had to prove using some steps demonstrating our work. All right, now we're going to look at inverses on the graphing calculator. So the calculator can only draw an inverse. It can't give you the inverse of a particular function. So we're going to use our calculator to draw it. And these are the steps right here, but I'm just going to demonstrate it right on the calculator. So we're going to open our calculator and we're going to go to y equals, and we're going to enter the function for which we want to draw the inverse. So my original function is x squared. I'm going to use the example of x squared. All right, and I'm going to go to graph. And if your graph doesn't look like mine, your window probably needs to be reset. So I would do zoom 6 for a standard window. And now you should be ready to go. Now the next step then is to go to second draw and choose option 8. So we're going to go to second, and we're going to press the draw button or the program button. If you notice, right above the program button is the word draw. So we have to go to second program. It's highlighted in red. And you'll see that number 8 is draw inverse. So you can either press number 8, or you can just go to number 8 and hit enter. And then we have to tell it, draw the inverse for what function? Like, you need to tell the calculator, is it y sub 1? Is it y sub 2? So we're going to go to vars. and we're going to go to Y bars. So we have to press that right arrow key to get to Y bars. And we're going to select the first option, which is function. We're going to hit enter. And now we're all ready to go. We can hit enter. And it's going to draw the inverse. Now, that inverse is not a function, but it is an inverse. Okay, so remember, when we talk about deciding whether or not a function has an inverse function using our horizontal line test, we would say this doesn't have an inverse function. It does have an inverse, okay, but the inverse is not a function. If you were to drop a vertical line, you would see it hits it in two places, meaning it's not a function. So summary methods of finding the inverse of a function, you can interchange the x and y coordinates. The graph should reflect over the line y equals x. And for the equation, we're going to switch the x and the y and solve for y. All right, that's everything I have for this lesson. Thanks for watching. Have a great day.